as always, a good point to start is an introduction. Could you please introduce yourself? What's your background? What are you doing right now?
Absolutely. Well, first of all, hi, everyone. Thanks, Sergey, for your invitation. It's a pleasure to be here. My name is Aitor Villar. I am a quantum engineer at SpeQtral, and I have a telecommunication engineer background, but towards my graduate studies, I moved to the field of quantum physics and quantum optics. So basically, my main focus during my research was enhancing the properties of entangled photon sources. So basically, experiments that can produce pairs of entangled photons. And in particular, we would like to, my focus was on building these sources for quantum key distribution from space. So basically, even though I went down to the fundamental principles and understanding the basics of entangled photon sources, I always had to take a design point of view related to the space, to satellites. So after a few years of pure fundamental research, the group in which I was doing my PhD here in Singapore at the Center for Quantum Technologies, we managed to build SpeQtral, a CubeSat mission that demonstrated entanglement in orbit. And now in SpeQtral, after graduating 2 years ago, now in SpeQtral, I'm basically pursuing the same path, but from a more commercial point of view. And basically, we're trying to sort of like facilitate the adoption of quantum technologies in our nowadays networks.
Yeah, thank you. And now, could you explain a little bit the technologies, because you mentioned entangled photons and how it's related to telecommunication?
Yeah, right. So our purpose for these entangled photons is mainly focused on quantum key distribution. And this is a technology that allows two parties to exchange secrets. So basically, when one thinks of encrypting communication channels, let's say we have Alice and Bob, there are different ways for these two entities to encrypt their messages. One of these protocols or ways to encrypt messages is a symmetric key, and basically this provides Alice and Bob with the same symmetric key. So Alice and Bob have the same secret, if you want, and basically if they use this secret of this key to encrypt and decrypt their messages, this communication will be totally secure. Now, the way QKD helps us is in distributing these keys. So you can imagine Alice on one side, let's say Alice is in Singapore, Bob is in Amsterdam, and we have somewhere, let's say in space, in a satellite, we have a source of entangled photon pairs. Now, this source will send one of the photons to Alice, the other photon to Bob, and if we exploit correctly the properties of quantum mechanics, Alice and Bob can agree on a random string of bits, on a random string of ones and zeros, that number one, if it has been tampered with, by somebody, this will show up in the statistics. And number two, they can be very sure that this is a random string of bits, and then they can perform their communication securely.
Yeah, so right now we're talking about quantum communications, but can you say what's wrong, let's say, with classical communications, and why do we need to go quantum for doing the safe communications?
Yeah, absolutely. So basically, this is all motivated from the kind of like the compromise or this in the near future quantum computer attack, right? So all these classical cryptographic methods that we have implemented nowadays, that we interact with every time we swipe our credit cards or we log onto the internet, the vast majority of these methods rely on public key algorithms. And basically, even though these systems have been, they've worked for many decades now, the reason why they are strong or hard to let's say break is because they rely on mathematical functions that are very hard to process. They're very easy to compute in one way, but very hard to be reversed, like the factorization of prime numbers. Now, classical computers, they take a big toll when try to factor in prime numbers, but quantum computers bring this advantage of insane speedups in calculation times and so on. So this is basically the main motivation for going towards a quantum solution in this case.
Yeah, and when the technology actually started and what's the current state of art? So how secure we can get, and yeah, pretty much what type of communication we can expect these days?
So going back to the very beginning of it, QKD, its first demonstration or protocol named BB84. This was reported somewhat in the 80s. Then really there was not much sort of like hype around it. Then early 90s, Aitor Villar came up with the E91 protocol, which basically allowed the implementation of QKD exploiting entanglement. And then I believe the early 2000s, so sort of like a boom of the field where basically everything was improving, right? The different protocols improved, the attacks that quantum hackers would perform also improve, and it's always this. There's a protocol, there's a mathematical proof that proves that it's secure, then a hacker comes in and shows, no, this is not secure because this loophole or this other loophole. And then something will happen, somebody will come in some research group and it will just improve the previous version. So this sort of like very exciting time, I believe, for QKD is already gone, but now the excitement is about making QKD commercially implement, be able to implement this in a commercial way and sort of like in a way that people will get interested about it, and clients and markets will be out there to implement these protocols in the networks, basically. Yeah.
So if I understand you correctly, what you're saying is that the research part is more or less done. Now we're coming to the industry era when we have to just start developing things because the research is kind of clear what you have to do.
Yes. So I believe that the research part of QKD itself, of this field, is done already, and now it's more about commercializing this product and be able to offer it to clients or companies or industries.
And so what are the main parts of these products? I believe because you said entangled photons, you have to have single photon sources and probably single photon detectors. So what type of technologies do you need to really establish this quantum QED?
Yeah, absolutely. So I just want to say something. QKD is not just, you can implement QKD with single photons. You can implement QKD with entangled photons. So basically there are different ways to implement QKD. Now, the technologies used range from laser diodes to nonlinear crystals to single photon detectors, and I can go on and on and on. But it's basically all these experiments, they all belong to the quantum optics sort of like realm. And nowadays, state of the art, you want to use. So in our case, we use lasers that are in the blue part of the spectrum. And then also this conversion, this spontaneous parametric down conversion that we perform, the wavelength of these photons falls in the near infrared. So we want single photon detectors as well in that region. So it all depends on sort of like what kind of QKD you want to perform, because you can also move onto the telecom wavelengths, and then your lasers will be different, your detectors will be different, and so on. So I would say like overall is sort of like a big quantum optics experiment, and one can expect technologies such as I said, laser, single photon detectors, nonlinear crystals, liquid crystal devices, lenses.
Yeah. And pretty much all these supporting technologies, they are very robust and ready on the market. So it's pretty much the main challenge here is to really assemble it into a device which will be suitable for quantum key distribution, right?
Pretty much. So I think it's fair to say that the market for these devices, for lasers and so on, is quite mature, quite developed. So one can find very good quality devices out there. And then as you say, it's more about you putting the pieces together, assembling everything, and sort of like tailor what application are you looking at. Because again, QKD in the lab, this was invented decades ago. Then people moved on to making free space links where they will link two locations separated hundreds of kilometers. So it got a little bit more challenging. Now the aim is in putting QKD devices in space, in a satellite that can have a direct line of sight, with your ground station, and this way you can span longer distances as compared to the case where on Earth, because it's an optical technology. So if you are using free space, you need line of sight. I think the record right now is about 400 or 500 kilometers. At some point, of course, the curvature of the Earth will not allow line of sight between two points. So there is a limitation there, and that's why space is kind of like the next thing to do.
Yeah, so and that's why you went to space, because right now you cannot really go a free space, or could you use a fiber, or you really have to go to space?
You could use fibers, but then at the same time, the limitation in losses will render your communication in, let's say, again, a few hundred kilometer distance. So again, I'm not saying that space is the only way to do this for your QKD application, but it does depend on your requirement. So if in a city like Singapore, where distances are quite limited, we are in a fairly small island, perhaps 50 to 100 kilometer fiber link could work. But if you are really looking into, let's say, performing QKD between two banks, one in Singapore, the other one in Amsterdam, where the distance goes in the order of thousands of kilometers, then free space wouldn't work, fiber wouldn't work. So that's when the satellite, the space part of it kicks in.
Yeah, and that was a challenge, and that's why you decided to go to space, right? Because I think it's quite different, let's say, industries or technologies. One, telecommunication, let's say, or lab research, and another one is space. So how you decided that it's necessary to go to space?
Well, because I think the bottlenecks were very clear from quite some time already, because the generation of entangled photons or single photons that are useful for QKD. So let's look at the laser. For instance, we know that the power available in lasers is not going to improve by a factor of 20 in the next, 20 years if you want. So basically, really the technologies that I was just talking about just now with the lasers and the detectors and so on, really reached a point of maturity where no more research efforts were put in that way, because we are already sort of like saturated as to how much we can get out of it. And really, if you look at space and you look at the properties of the atmosphere and so on, it turns out, even though it sounds daring, right, to have a satellite flying over your head and shooting these entangled photons, really, if you choose your wavelengths correctly, there are few transparency windows in the atmosphere that make this free space link. At the end of the day, it's a free space link. Just that one node is moving and the other one is the ground station is fixed. But really, it's a more than feasible implementation. And in fact, we've seen this a few years ago by the Chinese group that built the satellite meshes. They already demonstrated this that space to ground QKD is indeed possible. And now people are just trying to, get into do this in a more cost-effective way and just, be able to launch more and more satellites with this technology.
Yeah, and I guess it's quite different requirements. One thing, you have to develop a product which works on Earth, and another requirement is to develop a product which works in space. So what are the different, let's say, requirements and challenges?
Absolutely. Those two products might look as different as, night and day. So basically, let's take a laboratory as an example. Temperature is controlled. There are not many vibrations. You can get away with a table with few holes. It can be an optical table, but it doesn't need fancy stabilization, sort of like hydraulic legs or whatever. So you will make an experiment. You will put your assembly all together without thinking too much about things like, what if my temperature all of a sudden goes down 15 degrees, or what if I see a random vibration on my experiment? Because these things really don't happen in a laboratory environment, or at least they shouldn't. So the tolerances are very, I wouldn't say they are straightforward, but you can definitely work with this, right? So it will go down to coupling light into single mode fibers. So we know single mode fibers have cores of like a few micrometers, but still, buying proper components and doing things with a little bit of common sense, you can get away with it. Now, if this source needs to work in space, this is a different thing. You need to think of what environment your experiment is going to see. And let's say we choose some low Earth orbit in a diagonal with some inclination. So that means that 1/3 of the time, your satellite is going to be under the shadow of the Earth. 2/3 of the time is going to be under constant illumination from the sun. And there is no user that can go up there and realign the thing. So everything needs to be very robust, and that's when you are in orbit already. Prior to that, the experiment is sitting on a rocket that is gonna ignite, take off, and the vibrations there can be very, very dramatic. So there are certain envelopes of vibration that your experiment needs to be robust against. And basically it's thermal, it's vibration, it's radiation that you also need to take care of. If let's say you have single photon detectors in orbit, after a few months, the dark counts of these detectors can already shoot up so much due to radiation. So it's a number of things to consider once you want to go to space, for sure.
Yeah, and if something fails when with the things is spinning the orbit, you cannot fix it. You just give up, right?
You need to live with it. You have to live with it.
So you prepare,
yeah? No, basically what I wanted to say is that you just design everything with margins. You design everything with we wish we could have, let's say, 2 lasers instead of 1, right? Sometimes you can do that. But that's why you also test a lot your devices before actually going into the rocket and eventually going into space. So you have to do testing campaigns. You have to make sure that you comply with the rocket launcher sort of like requirements and so on. So hopefully by the time you are getting there in space, there is no room for surprises. But that's it can happen. Sometimes it can happen.
And how do you communicate to the source, to this spooky one? How you communicate to this? Because it's spinning the orbit and you sitting in your lab. So you have some sort of telescope?
Yeah,
or how do you do it?
Well, now that you mention it, actually, here I have a replica of Spooky One. So this is not this is a 1-to-1 model of the satellite that is currently orbiting in a LEO orbit. And so this is the final part of my PhD. I work in making these the payload. You can see here. So this is the entangled photon source with the crystals and so on. I want to say that this was not done at SpeQtral, but at the Center for Quantum Technologies in the research group of Professor Alexander Ling. So myself and actually some members of SpeQtral also work in this mission. That its main goal was to demonstrate quantum entanglement in orbit on a CubeSat. So as I mentioned, Missions already demonstrated this, sort of like in space quantum entanglement, but they used a very big satellite. So Missions is I think it belongs to the category of microsatellites. So it's the size of a small car. So they managed to fit many experiments, and one of them was a source of entangled photons. For us, this is the satellite itself. There is no extra module that I'm going to put next time. This is the whole thing. You can see the solar panels over here, and it's hard to see, but the antennas is this gold bar over here. If I were to take out the box, these antennas will ping, open up like this. And so back to your question about how to communicate, mainly we will use radio frequency to talk to Spooky, I think UHF, and then eventually, not in Spooky, but in a follow-up mission, you will have optical links. So the communication will be both via radio to establish certain housekeeping parameters, just make sure that the communication is there. And then when you want to transmit the entangled photon particles, that's when you establish the optical link. So the satellite and the ground station, they need to sort of like track onto each other to allow this quantum link to be implemented. Yeah.
Yeah, and let's maybe look again at the spooky one. So I see there is like lots of optics. Yes. Probably there are lots of electronics and I guess mechanical engineering. So what type of it was done in the research lab. So you were sort of master of all hands. So you were doing everything, right?
Basically, well, I was very lucky to be part of a very nice team, where I took care of the optics of the experiment itself. Then, of course, we had electronics engineers, mechanical engineers, people with experience in the space industry to put everything together. So basically, let's just go step by step. So this is the entangled photon source. This is the layout of the experiment. Here we have the laser. Then we have a bunch of nonlinear crystals. This is where spontaneous parametric down conversion happens. So this is where we produce these entangled photon pairs. And then you can see this sort of like L-shape, finishing part of the setup. That's where we have the single photon detectors. Because what we want to do is we create these entangled photon pairs, we separate them by the wavelength, and then we perform polarization measurements to assess the quality, the entanglement quality. Basically, we perform a Bell inequality violation, and we just see what kind of like value we get, just to be able to claim that we are entangled indeed. So the very nice thing about this experiment is that maybe you already see, but all these electronics over here, this contains all the needed electronics to run this experiment. So it has laser drivers, it has quenching circuits for the detectors. It can run, it's a bit hard to see, but over here, this black piece is a liquid crystal polarization rotator. So this is a device that we apply some voltage on, and with a combination of wave plates, we can actually perform different polarization measurements. Because unlike a laboratory environment where you'll be more than happy to just rotate one polarizer filter, mechanisms in space, basically things that move in space, if you can avoid them, you should avoid them. You don't want things moving around, rotating. So these liquid crystal polarization rotators are very nice to use because it's almost like a window that you install there. There are two cables, then you apply voltage, and then these molecules change their shape. And this allows us to perform, let's say, a measurement on the horizontal basis or in the diagonal basis. And it's very nice that it's all integrated in one single PCB. And with this microprocessor over here, it's as if it was a small computer inside this PCB, and you can just talk to it, tell it to run the experiment, now save the data, now run it again. So it's a very nice instrument indeed.
Yeah, but I guess it's not the first version, right? So probably you designed quite a few designs and tried, and this is like really a final version. So in the lab you prepare it, let's say, I don't know how many versions, actually how many versions, how complicated and how long did it take to prepare that, to release the final version?
Okay, so Alexander Lin started his research group, I want to say 2011 here in Singapore. But back then, almost 10 years ago, really to talk about quantum devices in space, it was almost like a talk for crazy people, right? So what happened back then was there was very little heritage. You wouldn't be able to go on Google Scholar and find papers about, oh, this guy put a nonlinear crystal in space and this happened, right? And then this person will tell you, oh, watch out for this, watch out for that. So there were many tries, many versions. So I said 2011, Alex started his group. I think I joined late 2014. So by 2014, 2015, we already started with our space tests, basically. So we started first using weather balloons. We will basically attach our prototype to a balloon, helium balloon, that will just go up. into the sky, and then at some point just burst, and the package would just like fall back on Earth again. That was really cool. So basically, we have very early prototypes there where we were just testing, kind of like a step-by-step approach. We're testing first the laser, then the detectors, then a laser plus a crystal, and things like this. Where with this approach, we made sure that we could check one device at a time. And like this, we were ready to have like a real space mission. I believe it was around that time. So I think the weather balloon test was around 2013, and then late 2014 we were part of this Danish mission, a COMEX-2 mission in the Antares rocket, and basically we just put a prototype in some collaborators' satellite. And then when the rocket took off, the whole thing exploded. So the satellite never made it to space. But interestingly enough, we managed to retrieve the satellite. It was just lying somewhere on the ground. It was on a beach somewhere in Wallops Island in Virginia. And to our surprise, everything worked. So nothing broke, and that was amazing. So we were very sad that the satellite never made it to space. But indeed, recovering the satellite a few weeks later and be able to switch it on and then just see like a slight change in the performance, that was just amazing. So even a paper came out of this explosion. So it was very, very useful. But
very robust technology.
Super robust technology. And so again, the nice thing to move towards small satellites like SpeQtral is that it doesn't take you that much time to build another one, right? So the duty cycle of this technology can be speed up like so much compared to traditional space or traditional satellite missions. So a year later, we had another prototype ready, and we joined the Galatia mission. So Galatia mission was another CubeSat mission from the engineering department in the National University of Singapore. So they gave us some space to put our quantum payload, and luckily nothing exploded this time. So we managed to get it from space. And back then it wasn't an entangled photon source, it was a correlated source. So basically we were just generating these pairs. We weren't entangled them as we did 2 years later or 3 years later in SpeQtral. So by the time we got to SpeQtral when we started with this mission was maybe 2018, we knew that if we look at the evidence from all our space heritage, everything should work. So we just we did some improvements to our source, and we just we put everything together, and very nicely this payload came about, and so we deliver early 2019. So if you really want to go from start to end, it's almost 9 years of development.
And how many people work on that?
So over the years, I want to say, I think it's safe to say no less than 50 people.
But okay, let's say that you want to design a new SpeQtral one. How many people would work on that, and what's, let's say, the time to build one?
Okay, so the main core, sort of like the main team was in total, it was about 12 of us. But then again, by the time I joined, a lot of these pieces in the optics, at the very least, some of them were already developed, so I could just sort of like take that design and maybe rethink if there could be another improvement to be done. For the electronics, have 50-50. Many things were already implemented. So we didn't, the team that really worked on SpeQtral one. We didn't start from scratch, of course, but we put good work in, and yeah, I think it was something between 12, 15 kind of like permanent grad students, postdocs, research assistants.
And what type of development are you expecting to do in the next, let's say, 5 years? What are you working right now?
So what I expect is to actually for the more on the satellite technology. Both the satellite technology and also the sort of like the ability to create the optical link. So we know that the quantum bits work. That's not an issue. Now what we need to do is to bring together the cost effectiveness of small satellites like Spooky and the ability to put a telescope in it. Because again, you're creating an optical link here, so you need to have some sort of aperture in your satellite, and you need to be able to point very finely where to send your quantum particles. So I believe it's more of an engineering challenge, and for now it's very state of the art. So basically there's no market, at least not a massive one for these technologies, but you can look at it as a laser comms, very, very similar. End of the day, it's an optical technology. You need to deal with telescopes, pointing, tracking, and so on. So I think really the next big thing is to make these small guys like Spooky ready to accommodate these technologies, because as nice as CubeSats are, they come with very limited resources. So for one, they're very small, so you need to miniaturize your technology. Then the solar panels are also very small, so you need to be very efficient in the power that you consume. And it just, the moment you go that small, everything, dimensional stability, thermal gradient changes, everything is just a little bit trickier. So I think once we get past that point and we can see constellations of these CubeSats carrying quantum devices, I think that's going to be very exciting to witness, for sure.
And you are developing as well ground stations, right?
Yeah, of course. So one end is the satellite, the other end is the ground station. Fortunately, I don't think there's any kind of bottleneck there because of astronomers and all these observatories. They've done most of the work. It's just you being able to capture quantum particles, which is just particles of light, and just be sure that you detect them in a very efficient way, that you don't destroy whether it is polarization, the polarization degree of freedom that you're working with, or anything. So I think the challenge is more on the space end rather than on the ground segment.
And let's maybe talk a little bit about the company, because I see there is a nice banner behind you which says SpeQtral. So actually, how did you start it? Because you describe really nice technologies, but at some point you realize that technology should go from, let's say, from a research lab to really a company, right?
Yeah, absolutely. So I believe SpeQtral was established at some point in 2017, and by some of my former colleagues. And then in 2019, we got the seed funding. So I joined them shortly after this sort of like milestone. And basically the aim for SpeQtral is to sort of like, take advantage of all this expertise and knowledge that was harvested in the university and make a product or implement something that is commercially attractive, that is commercially usable, because again, the principles of QKD are all demonstrated. Now it's the time about, can we use this? Can this make a difference in our society, the way we communicate, the way we secure our communications? So that's SpeQtral's sort of like main mission, to transform the networks that we have nowadays to the quantum change. And we just see this in a very positive way. It's not that we are running down the streets saying quantum computers are coming, watch out for this, but rather in a very sort of like, the infrastructure is there. We have optical fibers everywhere. We have satellites everywhere. We just need to be able to adopt these technologies. And as a first sort of like big step, we want to do QKD, be able to offer QKD services from space to ground. And this will allow you to sort of like secure two locations that are very, very, very far away. And in principle, you wouldn't be able to do this with optical fibers or on Earth free space links.
And what type of customers you expect to have, or maybe you do have, or you expect to have in the future? Is like big telecommunication companies?
So basically anybody who has a little bit of a concern in terms of data protection. So this can go from banks to hospitals or high risk buildings. So basically, and again, anybody who has a need of protecting data, which we believe it shouldn't be too hard to find, because again, the advent of quantum computers pose a real threat. And again, we are happy to. It's not that we're just focused on the space segment. We are more than happy to think of on ground QKD solutions, but this is also one of the different flavors that SpeQtral brings to the market, because again, we are not the only ones doing QKD. So you have big players like ID Quantique or Toshiba developing very nice devices, mostly for on-ground purposes. But since pretty much, I would say like 70% of the team here at SpeQtral comes from the university, from the Center for Quantum Technologies, we already have that experience. We are already ready to perform these, to build these devices for space, and that's what we're trying to do.
And what you say that 70%, let's say, of people coming from the academic background, and right now you're looking for what type of people you're looking for your team? Let's say that electrical engineer, mechanical engineers, what type of people?
So right now we are looking for software engineers and also electronics engineers. And this is kind of funny because people will think, oh, quantum technologies, right? It's all super, almost like magic. But at the end of the day, you are still, soldering these components. You are still doing like real, on ground, sort of like real world things. So basically, for now it's a software engineer and electronics engineer that we will be very happy to, to chat with, or just we have our email info@spectral.space. Anybody can reach out, and looking forward to talk to all these people. I think it's a very exciting time right now in this for this field for sure.
And if you compare, let's say, working more in the research lab or in academia, and you compare working in, let's say, in a startup on the industry side, which one do you like more and why?
So for me, my personal opinion, I really enjoy my time as a PhD. I really enjoy the going very deep into the detail of things, and which is basically asking like why. That I really enjoy. But I always felt that building things was the thing that motivates me the most, and build something from scratch. I do find some joy in it that is hard to describe. And then I guess it just, quantum in general just captivated me. And I do believe in this technology. And rather than, again, because the research part of QKD and so on is sort of like done, I didn't see myself sort of like changing topics, 100%. And I believe that, at the very least for the next few years, working on this technology can be very, I'm like super motivated. That's what I'm trying to say. And yeah, I think the industry here in Singapore is very, very exciting. The country in general believes in, in advancing current technologies, and there is many opportunities for funding. There is a lot of networking events. So it's something that is within the society, I want to say, or the workforce in Singapore. It's not like they don't want to live in the past. They want always to be at the cutting edge of things, whether it's quantum or AI or all these hot topics. So I think Singapore is a very nice place to to take this thing to the next level.
Yeah, and I guess my last question will be a little bit speculative. When do you think the quantum network will be literally full power and working properly?
Well, I mean, again, my guess is as good as yours, but I think 2030 doesn't sound like a too much of a bet to to have something that is useful already. I
20,
wouldn't say
30 years.
Sorry?
20, 30 years.
As in not in 2030, in 9 years from now.
Okay.
So I think by then, maybe not like a super full-fledged quantum network that is doing all the things that they promise, but definitely something useful. I think it's quite viable. That's again that's my guess. Hopefully it's sooner than that.
Okay, thank you very much. I think it's a good time to wrap up. I really enjoyed talking to you, and thank you for showing these very interesting devices. These devices are very close to my heart because I'm coming from the experimental background. So when somebody shows me a small laser which can operate at space, for me it seems very, very nice.
No, thank you so much for having me, Sergey. It's been a pleasure. Hopefully talk to you very soon.